We introduce Gear-NeRF, a dynamic scene representation that leverages semantic information from advanced image segmentation models for free viewpoint rendering and tracking. Our method takes RGB videos captured from a camera array as input. Our trained model achieves photorealistic free viewpoint rendering of dynamic scenes. What's more, with users giving simple clicks at any time and from any viewpoint, our method can perform free viewpoint tracking of the target object. Utilizing multi-layer perceptrons to map 3D coordinates and viewing direction to volume, density, and radiance color, neural radiance fields have achieved photorealistic novel view synthesis. To allow NeRFs to model dynamics, early approaches used MLPs to model a deformation field that maps all 4D spatio-temporal points to a canonical space and a network to render the scene from this canonical space. More recent approaches have achieved huge speedups by directly conditioning density and color on 4D spatio-temporal coordinates and using tensor decomposition techniques to compress the representation. NeRF-based representations have also been used to enable 3D scene understanding, including unsupervised object segmentation in 3D. Moreover, training a neural radiance field with the help of powerful 2D image models, such as the Segment Anything model, SAM, can also yield object-level segmentation. Similar to 3D embedding approaches, our method learns a 4D spatio-temporal embedding that maps a 4D coordinate into density, color, and SAM embedding. To save time and memory overhead, we use serialized 4D feature volumes to implement such a mapping. Our trained model can render SAM feature maps associated with RGB images from any viewing direction. Moreover, users can obtain object masks by simply clicking on a pixel on the object of interest from any given view. Additionally, our study shows that the introduction of semantic embeddings helps improve the rendering quality by allowing us to segment regions of the scene into groups called gears, based on the extent of their motion. To accomplish this, we start with a low-gear representation, applying low-resolution spatio-temporal sampling to model the entire scene, which yields a poor rendering of the scene. We then compute a loss map between the rendered images and SAM encodings and the ground truths, and initialize point prompts from high-loss regions. We feed the prompts and the encoding of the rendered image into the SAM decoder to get object masks. These masked regions represent underfit regions. We then perform a gear upshift of these regions, thereby increasing the spatio-temporal sampling resolution in modeling them. We repeat this process every few epochs. Here we show how an upshift in gear results in an increase in the sampling resolution. Additionally, by extending array from a clicked pixel into 4D space, we determine the object to be tracked by choosing the first point in 4D space with a high density. This point is then projected into the novel view, and the corresponding object is segmented out using SAM, a functionality not yet achieved by existing NeRF-based methods. Quantitative comparisons for both rendering and tracking demonstrate the effectiveness of our approach against state-of-the-art baselines. Here we show some qualitative results on free viewpoint rendering. Here we show some qualitative results on tracking. Our approach achieves state-of-the-art rendering and tracking performance on multiple challenging datasets. Please check out our project page. Thanks for watching.